Chris Barrow from WSP. So with no further ado, I'll let the presenters take it over. Thank you very much, Ken.
All right. All right, I'm going to do a little bit here at the beginning just to get us set up, I hope. We're gonna just this one. Okay, so I want to go over some definitions up front just to make sure that we don't get lost in kind of the soup of letters that is sometimes associated with these topics. And so you can see the agenda here. I'm going to talk about that for number one, and then Steve's going to take over why manage our system and what are other states doing. Chris is going to talk a little bit about the overview of the study, some of the potential strategies, and then I'll take it over again for a deployment analysis, and we'll go over the next steps. So very quickly, Transportation System Management and Operations, TSMO. This is the overarching umbrella of a variety of things that are designed to make the most of our system. So it's managing our system, and that's kind of the overarching umbrella. ATDM is Active Transportation Demand Management. It's the next rung down, and it's looking at actively managing things, and it looks at both the supply and demand sides. And this study has that acronym on it. But active demand management, active traffic management is kind of the next rung down, and that's really what we're talking about today, is trying to look at using information and helping on the demand side, giving people better information, and then looking at the supply side as well as managing the flow of traffic. So that means things like queue warning and ramp metering and things like that. So that's really what we're talking about. So I just want to boil it down so you can kind of throw out all the acronyms. Every time you hear ATDM, ATM, all this stuff, think strategies to manage the highway system. And usually we're using signs and striping and traffic control stuff that we use every day. And we're combining that with data. So that's kind of a new element. So that's basically what it boils down to. And I just want to kind of clear that aside before Steve gets up and talks about why we are talking about this at all.
Thank you. Thanks, Rob. Okay. Who in here has heard of TSMO before, at the very least? Excellent. Who has heard me or Sawala talk about TSMO? Okay, the message is getting out. This is very exciting. So, you know, the overarching question of why we're doing this can kind of be distilled down into the Department of Highways operational goals, which is to promote safety in all decision making. That's what we want to do in every aspect of the Transportation Cabinet's work, increase our economic opportunities and the quality of life of the traveling public. We want to, you know, have a relationship with the people who are using our roadway system. That's usually a benefit, but we want the roadway system to perform well. We don't want it to be underutilized. Some of our segments are overutilized. Does that all make sense? Why TSMO is, why this kind of stuff is important? Okay. One of the other biggest problems we have is that we, of course, have limited resources. And we're kind of boxed in a lot of different ways, especially on the interstate system, with the things on the interstates. Anything we do on the interstate system tends to be more expensive. And we are, in certain areas, we are very boxed in by right-of-way or other constraints that make potential solutions like, you know, just add more lanes, not very feasible. And of course, we know through the concept of induced demand that if you add lanes, it's very difficult to improve safety and reduce congestion by adding lanes. You are adding conflict points, and you are going to allow more throughput, of course, but there's more going on. That might not be the best thing to do. So if you are able to kind of use the pavement you have a little bit more efficiently, we sometimes see that congestion is, you know, a peak hour problem. Safety is usually an all the time problem. There are strategies that don't involve widening that allow you to use your system more effectively, is really what it boils down to. And so in a place like Northern Kentucky, where we have a lot of constraints, this kind of thinking, this kind of tool is a very good one to have in the toolbox, because there's, as Chris and Rob are going to talk about, there really are some things we can do to improve safety, reduce congestion, and improve the reliability of the system without our normal bread and butter of just add lanes. Everybody still with me? Okay. Now, a lot of this stuff isn't necessarily, we can still add lanes. That's of course still a very viable thing. No one's discounting that. It's just, we want to make sure that there is a tool in the toolbox that's not the only thing you do. Now, Kentucky's been doing TSMO-like things, or has been doing TSMO already. It's a very big umbrella. Things like safety messages on the side of the road. That's a TSMO solution. That's an ATDM solution. Dane Blackburn and I had the opportunity, as part of this project before it even kicked off, to go and tour the Georgia TMC, the Traffic Management Center down there in Atlanta, and got to see them do like their fancy things. They have a reversible express lane that on I-85, just both north and south of Atlanta. See them, move that control back and forth. Very, very cool. That's a sidebar. Anyway, so as you can see, our neighboring states, Missouri has a queue warning system. We have a queue warning system too. It's in Northern Kentucky right now. Safety messages on the DMS and travel time information. You get fancier as you get into Ohio and Georgia with ramp metering. The I-670 smart corridor there in Columbus has these really fancy, expensive overhead gantries there in the middle that kind of tell you what the speed limit is, what lanes are open, which ones you can use. And then they have also things like variable speed limits, dynamic lane use, and speed advisories. Now, like I said, Kentucky's got some exciting things going on in this space. Did anyone listen to Jason talk about the TSMO program plan this morning? Hands, please. Awesome. So you can see that this kind of thinking is really starting to ingrain itself into the KYTC process. Also knew this highway plan was approximately $7 million per year in various funds for TSMO and ITS, Intelligent Transportation Systems, which is a dedicated pot of funding for TSMO. Was something that really didn't exist before. Of course, we have deployments already with our travel time displays, both run by Trimark and run by KYTC. We've got this study, so this is something we're doing, and we're really starting to kind of integrate TSMO into project thinking, both in the planning, already in the planning phase, but also in the design phase. There was a request for, can we look at a reversible lane on an arterial? Can we do a managed lane on an arterial? We have queue warning systems, those intersection conflict warning systems come into this as well. So big projects, little projects, this TSMO stuff is coming into it. And of course, everybody knows there's a lot of data, and big data, very large data. It's sometimes a chore to work with. It can be information overload, but it really it allows you to have the data available to back up what you're trying to do. And you can see if it's actually working in nearly real time. You can put some of these systems out, and based on the agreements that we have with certain data providers, we can see if it's actually working. We can see if it's doing what we want it to do. And so that leads some states like Georgia, they don't model anything anymore. They don't put these kinds of solutions into a micro simulation. They pick a spot of road and they do a test run and deploy it. They demo it, and then they see if it works. And then if it works, they're just going to put it in the bigger system. It's a different way of thinking. And with that, I'm turn it over to Barrow to talk about the study.
Thank you, Steve. So I guess the section of the study that I'm going to talk about is kind of give you the high level overview of what we did, what we were looking at, what types of things we wanted to cover. And then Rob's going to get a little more into the details about the level of depth that we got into for some of the analysis. So I guess the first thing, big picture of this study, what we were trying to do is, get the most out of the existing assets that we have. We've spent if you heard in Jason's presentation, if you hadn't heard it, or you'll hear it in the afternoon, we've invested billions of dollars into a system to move vehicles and help provide mobility. All we're trying to do with this technology piece is maintain the investment that has already been produced. So the first thing we were looking at is, identify and investigate what's happening on the interstate system in Northern Kentucky. What are the types of things that are causing the issues, and what might be some solutions that are low cost, easy add-ons to the existing system to help improve benefit and also kind of set a path forward for what Northern Kentucky and the rest of the Commonwealth is going to look like in the future. So a part of the process is also engaging with OKI in the district and some of the other cities. If you guys don't know, Northern Kentucky's got a unique situation where there's a lot of little small patches of cities right along the river. And so having them included was important. Evaluate what some of the options are, also what some of the potential benefits were, and then really identify and set out the plan for, hey, what's the next step? What's the easiest thing to do today? So really quick, in general, this type of study is a little different than a traditional planning study. We got the traditional planning study across the top. Whenever you start bringing technology into the picture, you want to have a real clear understanding of what's the goal? What am I trying to achieve? Very similar to a planning study, but then getting into how do I want this thing to operate? What am I looking to achieve? Once you get that nailed down, it's moved to the next phase, which is, okay, what are the types of requirements that I have to have with the system? And then you get into construction. And then after construction, there's a whole bunch of testing and integration that you got to make sure that's going on. It's got to work. It's got to do everything that you said you wanted it to do. And you have to verify along the way. It is not as simple as putting pavement down and just going and turning around and seeing what happens. So some of the goals that we had for this study: reduce travel times, reduce crashes, improve travel time reliability. And we're really looking for, a favorable benefit cost ratio so that we're showing, why we need to continue to invest more into these strategies. And the things that we were looking at, the considerations that we had to be careful of is, the physical infrastructure, what's actually out there in the system from a connectivity standpoint, communications, power, existing infrastructure, how much money that we have. And then also, you can't just put this in and walk away and then come and look back at it in 15 years and go, the pavement condition's still good, we're good to go. This is a daily thing that you have to be on top of, thinking about, checking on, and making sure that it's still doing what you intended it to do. So real quickly, going to run through just the range of potential strategies that we looked at. The RFP had a pretty nice long list that we tried to narrow down. I called it everything but the kitchen sink when I saw it, and was hoping we didn't have to do everything because it might not make sense. But we used that funnel and moved it down the process. So the first one that we had, dynamic shoulder use, and so using electronic signs to dynamically utilize the shoulder for a travel lane. Normally, this is done in a peak period condition. It's not all the time. It's really just when you need some more capacity. But the things that you got to understand is, one, how you're going to do it. Is it going to be a smart lane where you have a dynamic sign, or is it going to be a static sign? So we got just an example of, something from Georgia, where they actually have a static sign that opens the lane from 8 to 10, and then again from 4 to 6. And then over in Washington, where they actually have a dynamic lane use, where they have a green arrow, red X type thing. All of these systems require very similar things: communication, power, and thought on where they're placed along the system. You got to give people enough time to be able to make an informed decision and do something about it. So you can't just throw these everywhere. You got to think about how much time do they actually need, how much spacing do we have before they need to make a decision, so that it's something that people can do comfortably, because this is a lot more information that's just being thrown out there, that we try to make it as seamless as possible, but that can be a challenge, especially in some urban corridors. Ramp metering is another one that it's using traffic signals to basically break up the flow of vehicles entering the freeway. It creates a safer merge condition, and also can just help smooth out vehicles entering the freeway and just the flow. I like to talk about ramp metering. Just think about the plumbing inside your house. You can't put too much on at one point. You have to make sure that the system can handle what you're putting into it. And the whole point of ramp metering is just making sure that you're monitoring what's going in, how it's going in, so you don't have so you don't have a backup. Some of the biggest concerns with ramp metering that you just have to be aware of is the geometrics that come with it. What's your acceleration distances? What are your required acceleration distances? Hint, the Green Book requirements are not exactly what you need to be doing when you're thinking about ramp metering. So look at what a peer state has done. There's a lot of states that have gone out there and come up with their own, kind of acceleration distances that are needed for installing ramp metering. The discharge, how many lanes do you need? You really got to understand how many cars are coming onto the ramp, and it's not at an ADT level. It is at a 15-minute, 5-minute interval. You have to know when they're coming, how many are coming, so that you can control the situation. And then corridor application. The biggest thing that I see is a lot of people think, oh, well, I can just put ramp metering in a couple spots. You really got to, it's a system-wide approach. So you want to look for an opportunity to apply it across the system so that you can gain that benefit of moving people along the whole system. And again, communication, vision, cameras, and power are all things that you got to look at in right away for this type of system. Dynamic lane use control is another one that we had, and it's very similar to the dynamic shoulder use, except for it's really monitoring and providing information above each lane on the freeway. So where this really comes into play is if you think about, you have an incident, blocking a lane, providing people with the information a couple miles in advance, and every mile or so as they're approaching it, or half mile, depending on the spacing, is going to allow people to get over and out of the way instead of just running into the back of the incident. In certain jurisdictions, they also include speed, and that's another one that we're talking about actually 2 from now. So Q warning is the other thing, is just using the signs that you have out there to let people know, hey, there's an incident, just be aware. Understanding where these are placed. Again, you don't want to have one of these every 20 miles ideally, because incidents happen along the way. And so it's really critical to just understand, how the level of deployment that you need to have in order to get the message across to actually make a change for the safety of the system. And so this is another thing that we looked at, and the common trend that you might be seeing here is, man, Chris, Rob, you guys are telling us a lot of stuff that includes a DMS and a DMS in fiber and power and communication, maybe in some cameras that verify things. That is a lot of what we can do to lay the foundation and build from there. The dynamic speed advisories, another one that we looked at. The point of this system is really just to kind of mellow out flows along the freeway. It's another way to kind of tell people, hey, there's a change in the condition ahead. There's also 2 types of these advisories. There's a dynamic speed limit, which is controlling and could be enforced if you had legislation. There's also the advisory piece. So the advisory piece sometimes comes in from a road weather management situation. If you had a curve, or if you maybe had a really steep downhill slope on I-75 going into a river, letting people know, hey, slow down. The conditions normally are, 65 is fine, but it's 9 o'clock. We really let's target 45 miles per hour because there's just so much going on. So again, same thing here. It's all about placement. It's all about communication, power, and just thinking through where you put these signs. Another one that we were looking at was comparable travel times. One of the really nice things about both Louisville and Cincinnati is the options that you have available. There's interstate options. There's also significant arterials that run through these regions that you could use if you had an incident on the freeway. And so providing that information and really looking at, hey, what are the normal travel patterns? What are the alternative options that could make sense? These types of signs are the things that are just getting information out to the traveling public. And that's really what we're trying to do with all these, is to let people make an informed decision. That informed decision might be, I need to turn around and go home and just work from home because I don't want to drive 60 minutes to get across the river. So of all those strategies and a couple other ones that we had, the ones that move, this is the ones that advance. Yeah. So I saw the X and I was like, oh no, I messed this up. No, what moved forward was the comparative travel time, the Q warning, the dynamic shoulder use, and the ramp metering. The ones that were limited were the dynamic lane use control and the speed advisories. And the reason for that were some of those limitations, and mostly the dynamic lane use control and the speed advisories are going to require a significant amount of infrastructure that we don't currently have. from overhead gantries at half mile to 3/4 of a mile spacing, depending on what the policy this decision is. You know, it's just a lot of money. But what we do have currently in the system is we have some DMS out there. We are used to working with them, and we've actually got some pilot projects that that Trimark's been working with from the Q warning system on I-75. And so we're really looking at identifying things that could easily grow from there. But the biggest thing with this study that's very different from other studies, which is actually very similar to what the previous presentation was on with HSIP, was the amount of data and the level of data that you get into when you're looking at these types of things. Again, ADTs are not going to work when you're talking about an operational condition in a peak period. We've got to get down to, like Steve was talking about, with the big data. We can see at 2-minute intervals right now with the probe data that we have can have an identification of, hey, we've got a problem. For right now, we can use that if we can integrate it into our ATMS to provide information to these signs, and that will give us an immediate benefit. What do we need to do right now? We just need more signs. We need more signs in the right spots, and we just need to be able to expand the demonstrations that we have already. When that provides benefit, then it's a lot easier to go, hey, this has worked really well. Here's the benefits that we have. We have fewer secondary crashes. We have better travel time reliability whenever 75 does get shut down, because people don't just go to 75, they use 471 and 275 or the streets in Covington and Newport. So these are the types of things that, using the big data, understanding what's happening, having that baseline information, but also really looking at operational data when you have an operational issue that you're trying to fix, that's a little different than your normal traditional corridor planning study. And with that, we'll hand it over to Rob to talk a little bit more about the analysis.
So we're actually going to need to do a quick transfer. And so I'm going to take, a little unusual, if that's all right, we're going to take a couple of questions now for Chris and for Steve on their parts while I quickly adjust this. And
so any thoughts on the applications? Did we miss anything? You can throw as many darts as you want to. It's not going to hurt my feelings. I work with Jason and Steve all the time, and they're really good at doing that. So they keep you on your toes. So anybody? Beth, you got a question? I don't get a question. No, that's good. Yeah. So another thing that Jason talked about, which is I think critical, and why we've kind of taken the approach that we've taken through this study, is credibility. When you're putting in a system, having the system be credible is critical to people actually using it and, you know, changing their behaviors based on it. So that's one thing that we're looking at, is let's expand. Here we go. Sweet. Expand what we currently have, what we know works well, and just put it out there more, so that we start that baseline of, you know, what is credible and what's working. You can think about your questions and I'll answer them later.
Thank you. Yep. Thanks for that. All right. So yeah, we've talked a little bit about the data, and there is the data that we use, and there's the data that would run the systems. This is some of the data that we use. We use speed data that shows speeds on the approach to the Brent Spence, morning and afternoon. In the morning, drops off, actually increases as you approach the bridge. In the afternoon, you see there's big pink bands, shows that it's unreliable. You really don't know what you're in for in the afternoon. It could be that you're going to go 60. It could be that you're going to be down at 30 or 20. So we looked at that information. We looked at various maps. We looked at where all the crashes are. We looked at origin destination information, which is now even more available here in Kentucky to us, which is fantastic. So how many people actually do what Chris was just talking about? They actually divert over to 275, 471 instead of going over the Brent Spence. And we have all of that information, and that factored into the analysis, along with a lot of other things that we won't go into all the details, but feel free to ask questions at the end if you're interested. And that focused us. We were able to focus, okay, this is the part of the system we really need to pay attention to. This is where we can make a difference with these kinds of deployments, working with what we have out there already, and kind of building on that. So going to go through those 4 things that advanced. And I will say the big red X, that one deployment showed the thing that advanced was the hard shoulder running, and then the things that didn't advance, which was the lane control and advisory speeds. That's why there was the big red X that kind of showed what we decided not to move forward with based on the initial work. But these 4, comparative travel time, and then the other 3, they all advanced. And this is the deployment that we ended up examining. And it is not super complicated. It's basically 4 mainline dynamic message signs on the approach to the 275 interchange, and then some arterial dynamic message signs before you get on the system, so that they can also give you information that would be useful in making routing decisions. And in particular, all the orange locations, the main line, and then the interchanges near the system interchange, those would be a phase 1. That's where we really want to influence people's driving behavior. And we looked at that origin destination information to find out more, and we were able to make some reasonable assumptions about how we could influence people's behavior. And we also show that this can be done on using full dynamic message signs, upper right, or you can do something that just has inserts, much lower cost. So we've assumed for this study, the high cost, you could do it much less expensively than I'm about to show you. And get an even better benefit cost ratio than the 9 that, 8.8 that we've already got. And we tried to be conservative when we looked at all the benefits that we can get from communicating this information to drivers. And we really just focused on peak time, really the AM peak, but there'll be benefits all the time, whenever there are incidents in various times. So if you, that you don't really know what you're expecting, again, in that afternoon time period and even on weekends. So this, from a feasibility standpoint, this deployment doesn't require any right-of-way. The data is already available. It's like Chris was saying, it's signs, communication, power, basic stuff, so that we can communicate with our customers better about their options. And the cost is a little over $3 million, and we think that there's substantial benefits. We looked at 10 years of benefits. We think you basically going to recover it in a year or 2. It's not going to take long to recover that. That's why you get such a high benefit cost ratio. So, so that makes sense to move forward. And again, we use the high end cost for those. It could be even lower. All right. So Q warning is the next thing that we look. Oh, I want to just say, so this is already being done up there, but right now, what happens is when there's congestion, the message board that displays this information switches to safety messages. And so it doesn't show the message when you kind of need it most, because it's got a higher priority safety message that it needs to display. And so what we're trying to do is just we need to have dedicated signs for this particular deployment. All right, then the Q warning is all of the red signs that you see there, and is basically to build on the system that's out there, but increase the sign density so we can have a bigger impact and really let drivers know when they need to slow down and not have long gaps between the signs. Again, the queue moves, and drivers are often struggle to understand distances when we give distances. So just being able to give them better information closer to where they need to slow down is very helpful. So that's the general deployment there. From a feasibility implementation standpoint, again, no right of way, the data is already there. We're already doing this, but we want to do it better. And we want to do it more universally in all the areas where there is the congestion. And you can see again that the cost is around $5.5 million. And with the benefits, of both safety and travel time benefits, we think the benefit cost ratio is 5. It's going to pay for itself to the users fairly quickly. And it's not neither of these deployments are beyond something that we can do now. Now I will say both of those deployments, I've kind of painted the bright picture. They do require ongoing maintenance and operations. You have to pay attention to them. They're going to need some ongoing attention and investment, but it is not overly large. So, all right, so those are the first 2. We see those as pretty low-hanging, pretty much low-hanging fruit to improve this system. The third one is ramp metering. And this we looked at 7175 northbound, 471 northbound, and 275 eastbound. Those were the directions where it appeared that it could offer the most benefits. And when we ran through that analysis and looked at, again, how it would impact the flow and safety, we determined that there are definitely benefits, especially on 71, 75, that there, the cost is roughly $2 million and the benefits are substantially greater than that over a 10-year time period. We also did look at the feasibility. So up at the top, we looked at the issue of queues. It's very sensitive. It's a real issue. And we looked at the potential for widening the ramps. You would likely need to widen some to 2-lane ramps, like the figure on the right, to make it work effectively and make sure that the queues don't spill back. And you'd want to coordinate signals. And again, these are things that we can do. They're tools that are available to us. And so this one also held some promise. As far as our work, it looked like 71, 75 was the most promising and had the fewest issues. 471 has some shorter ramps and short auxiliary lanes and various things, just a little bit more complex, but also feasible and also has benefits. But it might make sense to do them in that order. As we worked through this project, one of the key things was we wanted success. We definitely don't want to roll something out and have it not work as advertised. So we've got, that's why the comparative travel time and then the queue warning, and then the ramp metering, it's kind of in order of level of complexity and building our system, building off of what we have and keep building the system and keep giving drivers better and better information and managing the system. So the fourth one is dynamic shoulder use. And we looked at all various locations where it would make sense with congestion. So 71, 75 northbound, 471, we actually looked at even southbound 471 that approaches 275. And we're talking about literally using the right or left shoulder. You can do either, and that is the deployment. And you would use it during peak periods generally. And it would provide additional capacity with limited widening. Typically, you don't build a whole nother shoulder. You use the shoulder, and you have for a certain number of hours a reduced shoulder along that shoulder use lane. And from a feasibility standpoint, there would be a number of very tight locations. There would be locations that would require design exceptions and potentially widening to kind of meet some minimum safety standards. So it would be challenging. It's not that it's not possible, but it just would be challenging. You can see from the cost, it would be much more costly than the other ones. It's kind of a different scale, a different level of magnitude. And it would require, second bullet down, 24/7 maintenance and operations. You have to pay attention all the time. You have to make sure it's clear. It is unlike the other three in that it requires much more active management. And it, from a safety perspective, the research is fairly clear. It can decrease crashes, and I'll explain why in just a minute. It can also increase crashes. It kind of depends on how many hours a day you operate it, because if you do some widening to accommodate that shoulder use lane, then whenever it's not in use, you have a very nice big wide shoulder. And so for all those hours that it's not in use, you've actually improved your safety condition. But then when you're using it, if you now have a very narrow shoulder on that side, for those hours, you have degraded your safety. And so the balance of those two things determines whether or not from a safety perspective, it actually gets better or gets worse. And so it's a little, that's why we put NA for safety. It's not that we didn't pay attention to it, but it would get down to the details of how many hours and how it's working. And it is harder to look at. We were able to quantify all the travel time stats pretty easily. Yeah, right. Yeah, good. Go ahead. It's a team effort here. They don't want to hear from just
what was interesting on this one, and we heard this all along the way, is why it's a 3.1 instead of less than 1. Years ago, whenever they were widening 471 originally, they thought about the structures and they're like, we don't want to have to come back and redo these in the event that we need to widen. So they spent the money decades ago to go ahead and have that out there. So that is one of the reasons why the cost is a fraction of what the other alternatives are, because you actually still have that geometric, that the physical space is currently there to be used. So just didn't want everybody going, hey, 3 point, that doesn't make any sense.
Well,
You got a line.
That's part of it. And then the other part is that was, if you look at the map, it was a shorter section. And actually, so this is one of the challenges is you find something and you think, hey, this could work. It actually might be better suited. And we had a lot of discussion about this as just doing we're still allowed to add a lane, right? We're still allowed to add a lane. It's just one interchange, the next interchange, and maybe we just add the lane and then we get all the safety benefits and everybody gets to use it all the time. So we've kind of gone back and forth. So there's, again, it's not that this isn't something that should continue to be looked at, but it didn't rate like the other ones. Clearly, the other ones have a lot of potential. This one has a lot more feasibility issues. All right. So this is the quick summary. Comparative travel time, key warning, ramp metering, the dynamic shoulder we just talked about, high cost, limited benefits. And I want to just touch on this before we end. Concept of, unlike other studies, we did a concept of operations for this. That includes looking at the current system, what's out there, what equipment, users, who's doing what are the policies. Then you got to justify what you're proposing. This is what we're proposing, this is why. And then you put together the concept of the proposed system. You write some additional details. How does this work? Because again, this is not like some of the other projects that we do. It's got a lot more things that are interrelated in different users. And then you do operational scenarios. So you say, I'll just pick scenario 3, off-peak minor incident. What happens? Who talks to who? What information gets transmitted? How does this actually work? And so this concept of operations outlines everything all the way to that level where we actually run through these different scenarios and look at what how the system will function in those scenarios. All right, and that takes us to back to this V diagram, which is kind of, I mean, it's kind of, I don't know, it's there's a lot there, but I pulled out the next piece, which is system requirements, high level design, and then the detailed design. And that's where this goes next. If it advances, is to looking at those kinds of those things and getting those system requirements set. So that is kind of the next phase for a project like this. And then, as Chris talked about, you get the bottom. The bottom one is where you actually deploy, you implement, you put the equipment out there, and then you have to work your way back up, testing it, checking it out before it goes live. You saw the Tennessee signs were blank. They just installed those. They're got to get it ready, and they're just starting to get to that phase. So they are working their way up the right-hand side down in Tennessee on I-24. So they're doing the verification, validation steps, and that is it. And so I got the 5-minute warning. So what? Yeah. Questions? So I will. Steve, did you stood up? You want to answer that one? Okay. So yeah. So it does come down to, yes, education. Yeah, education and enforcement, and driver familiarity with the system. But it is an issue. But if you enforce it and you make it clear that there are consequences to that, there are also risks to them from doing that. But it is an issue, and that's why it requires this ongoing management and cameras. But it is done up in Columbus, in DC. There's a variety of places, and you can get the compliance. It's just it takes active management. Yeah. So, other questions?
Back on that, are there any
Do you? I don't know. I don't think so. Yeah, I'm not aware of any. But
The biggest challenge we would have regulatory is and one reason why it was limited was the variable speed limits. Because we cannot set variable regulatory speeds. Right now, we can only do advisory speeds, which are not as effective if you don't have the enforcement.
assume that whole, infrastructure, depths, ramp, that's, those sort of things were already for some of these, concepts or design cost actually. Construction.
Yeah.
Yeah, that was another reason why, asking about some of the existing conditions, pavement widths, depths, were they included in the cost? Yes. And that's where that 471 example of the southbound, it was designed full depth pavement. It wasn't just designed partial shoulder. So that is one example of it. From the ramp metering side, to your question about, the widening, there's different ways to actually, different states do it differently. Some people have a full depth shoulder, and that was a discussion that we've been having with GDOT, is to actually modify their design standard to just go ahead and do that, because they have ramp metering across their whole system and they're continuing to put out more. But also a lot of states that are putting in ramp metering that might need that extra lane in order to minimize that civil cost. You just know that in 5 years, we're probably going to need to maintain that shoulder. And then also there's things to put up signs where like trucks only use the left lane, the normal shoulder, to help address some of those issues. But it was all considered.
I'll pick Artemis.
Go ahead, Chris.
Artemis does not currently exist. Ohio centralized all of their TMC operations into Columbus, and at that point, KYTC added the Northern Kentucky traffic management to the Trimark contract. So Trimark is currently responsible for the TMC in Northern Kentucky.
But to add on that, this would build on what they're doing right now, what Trimark is operating up there right now. They're part of that conversation. What happens to what happens with them if additional signs are added to what they're doing. And so we had those kinds of conversations. So it would tie in. We don't have the fiber and everything that we would like up there. So we would have to work through communications, would be an important part of this, but they're working through it now.
You could the questions about inside shoulder versus outside shoulder. We looked at both could work. You've got concerns with your spacing of entrance ramps and exit ramps on the outside shoulder. Inside shoulder, you might have to it might have a break point in it that might make changing lanes very difficult. And so those things we looked at both of them. I think most of the time it was the inside shoulder, right? Yeah. We did. They were part of our stakeholder group with emergency management and both our emergency operations center and the state police. It's early discussions there. When you start really getting into the nitty-gritty on designing a system like that, it only works with stakeholder collaboration. And so since this was just kind of a first look feasibility study, we didn't get quite there quite yet. We didn't want them to get excited about something that might not happen. But as those systems get developed, it's critical that we do.
All right, I think we've consumed the time.